Hi, my name is Ranko, and this is a talk about the error law for the fully mixed ground state of local Hamiltonian with good AGSP, which I'll explain in a bit. This is joint work with Itai Arad and Rahul Jain. Okay, let us begin. So we discussed local Hamiltonians, which are Hamiltonians defined on lattices, where on each side of the lattice it's a Hilbert space of dimension D. The Hamiltonian is a sum of local terms, where each term is supported on a small contiguous region of constant, which is constant. And here you can see an example of nearest neighbors Hamiltonian. And we say that the Hamiltonian is gapped if the energy difference between the ground state energy at the first excited state is order of 1, meaning that it is lower bounded by some constant which is independent of the system size. Okay, we specifically studied ground states of such Hamiltonian. There might be degeneracy of the ground space. So here we just specify some ground state, and later on we specifically address some ground state. So we study the entanglement correlation within the ground state, which is for our purposes. And suppose we cut the lattice to a bipartition, or left and right bipartition. We studied the mutual information between the left part and the right part. This mutual information is the sum of the entropies of the marginals subtracted by the overall entropy. So it also gives an upper bound for the correlations in the systems given by the Pinsker inequality. So we now focus on two behaviors of the mutual information with respect to the region. One behavior is the volume law behavior, where the mutual information scales like the volume of the region. This is just the number of sites. And the second is the area law, where the mutual information scale like the volume and like the boundary, the size of the boundary, rather than the volume. And why do we focus on these two behaviors? First, the volume law is actually very generic property of Hilbert space, meaning that if you pick a random pure state from the Hilbert space, it will most likely satisfy volume law. This means that this is a typical behavior, and moreover, ground states are not that typical. Ground states, specifically ground states of gapped local Hamiltonians, tend to satisfy an area law. This means that they are actually not that generic. They might have a very, very local, nice structure. And moreover, they are actually believed to be approximated by some good representations like tensor network. I will not go deeply into it, but if you are interested, this means that you can actually have a description of the ground state, which is polynomial in the system size, and therefore you can keep it in a computer. So the area law conjecture, which means the ground state of gapped Hamiltonians, have an area law, had a few attempts to prove. For the unique ground state case, where the ground state is unique, it was proven in 1D, in these two references, where the mutual information was bounded by some constant. This is in 1D, the boundary of the region is a constant. Okay. And recently in 2D, it was proven for frustration-free systems and locally gapped. Meaning that the gap of the Hamiltonians is subjected to any region is uniformly bounded. And Anshu et al. Showed that if you cut the 2D lattice in a vertical cut to left and right part, the vertical cut has a length of n, and the mutual information is bounded by n to the 1 plus some annoying additive factor, which is small. The area law conjecture was can be generalized to slightly degenerate ground state if you have an R-degenerate ground state, meaning the R is the dimension of the ground space, then you get an additive factor to the mutual information, which is logarithmic with the degeneracy. So what these bounds are interesting when the degeneracy is polynomial in the system size, but if it is exponential in the system size per se, they are meaningless. They are trivial bounds. So what happens to degenerate ground spaces? Really degenerate ground spaces. For example, when the ground degeneracy is exponential in the system size, in such cases, the simple question you might ask yourself is, does any ground set have an area law? And the former results I showed, any ground set had this area law. Here, if you think of this question for a little bit, you can very quickly reach to the no answer, because there is a very rich a ground set manifold, and you can easily pick some ground set, which is very, very complex. Give you a very simple example. Take a 1D lattice of 4 bits, qubits of local site 4, and take a local single site Hamiltonian where each local term kills just the 2 and the 3. The ground set is just a 0 and 1 manifold on each qubit, and this is just the full qubit Hilbert space. You can construct any such state on this ground set, specifically also some volume law states. So what we understood that we need to pick a ground state. Sorry about the presentation. So we understood there is a ground state, but we asked ourselves how a priori we can indicate which ground state will have an area law. So the quick answer for that, okay, sorry. Not a quick, what we answered in our work is that the ground state that we chose and we showed an area law for is the fully mixed ground state. This is just the normalized projector, which gives an equal weight to each ground state. This ground state has a lot of motivation why to choose it, and I specify two points here. First one is a mathematical point. It is a function of the Hamiltonian. It's actually the only ground set which is a function of the Hamiltonian, because the Hamiltonian is local. It has a local structure, and therefore this ground set will inherit the locality of the Hamiltonian. The second point is the more physical, is that this ground set has a very important physical significance. It is the zero temperature Gibbs state. For instance, Gibbs state is this state I wrote here. It's the inverse exponential of the Hamiltonian, and with beta is given by the inverse temperature. And this state is supposed to describe systems in thermal equilibrium. When you take beta to infinity, meaning the temperature to 0, you get omega, the only eigenspace that lasts is the ground state. So Gibbs states actually do have area law. It was shown in a few papers that the area law, the mutual information is bounded by the boundary times beta. Okay, and it was improved to some power of beta, but still, when you take beta to infinity, these upper bounds are useless. So a different technique must be used. Moreover, we know that when you approach the ground state, the quantity that dictates the area law and the mutual information and correlations is the gap and not the temperature. So the gap has to set in to this result. So what we did is we applied the AGSP framework, which I will now describe, to fully mixed ground state. This is the framework used to prove the unique ground state area law. And to give you a glimpse of our result, we showed that for 1D gap Hamiltonian, the mutual information is in 1D is bounded by the logarithm of the region. This is not exactly an area law, but it is believed to be tight. Okay, so this is a glimpse of our result. I will later describe it in a better way. So now let me cover a little bit on the AGSP and framework. The proofs for area laws in 1D and 2D cases uses the approximation to the ground projector. It used an operator which approximates the grounded projector. This could be seen per se as a function of the Hamiltonian. It's a polynomial of the Hamiltonian, Chebyshev polynomial, more exactly, and with some modifications to the Hamiltonian and to the Chebyshev. And I will not go deeply into it, but you can see it in annual stock and the previous stock. To define the approximate grounded projector, we say that K is a d delta AGSP, approximate grounded projector, for if it fixes any ground state, it shrinks the orthogonal part by a factor of delta, and it has a Schmidt rank D. So roughly speaking, D is the amount of entanglement that is generated by K, and delta is the rate it approaches the ground state. So these two parameters define how well is the AGSP, and to prove an area or not AGSP with a fifth, we need a good one. A good AGSP will be one where the product of these two is smaller than half. Largely speaking, is that the convergence to the ground space is faster than the entanglement generation rate. Okay. By the way, you can take powers of K and get this half factor smaller than any number. So to get an area law, this reference I showed you before constructed the AGSP for 1D gap Hamiltonian and 2D for station free locally gap. And they showed that if you have such a good AGSP, then you are guaranteed to have a product state with a large overlap with the ground state. This is very nice because to get an area law, you just take this product state and you apply multiple applications of the K operator, and you approach a ground state at the end, and need to perform a very delicate analysis of the convergence rate at the ground space with respect to the rate of entanglement generation. This is called the bootstrapping, the lemma I showed you. And what we do in our work was we generalize the bootstrapping to the mixed state case, the fully mixed ground state. That is largely what we do. Okay, so we actually show it for a better quantity than the mutual information. We show it with the maximum information. To recall, mutual information is just the relative entropy between the state and the product of marginals, which is also given by the minimum over all product state. And D is the relative entropy, it's the regular relative entropy. You can, if you want, you can generalize this and just replace D with some other relative entropy. We chose the maximum relative entropy. It was easier to work with. And to give you a glimpse on it, it is just if you given two probabilities, classical probabilities distribution, it is the maximum relative entropy is just the number you need, or actually the log of the number you need to multiply Q with to get it upper than T, than P. It needs to be above P, and the minimal such T is just a maximum information. Is just a maximum relative entropy, and the mutual information, the maximum information is just this definition replaced with Dmax instead. This is actually an upper bound for D. It upper bounds all René mutual information for already parameters between 1 and infinity. Therefore, it also upper bounds the mutual formation itself, which is good. It's a better upper bound. And however, it is a hard property to work with because it's not smooth. It's like the Schmidt rank. To handle it, we choose the smooth version of it, which is just the minimal maximum information in the epsilon ball around rho. Okay, this smooth version of it, it is related to the mutual information. This is subset theorem. It is related to communication complexity of single shot protocols. Okay, and it also gives you an upper bound for the mutual information itself. It disclaims in this claim. Very easy to prove. It uses the continuity of the mutual information and just the upper bound. So our main result is as follows. Suppose we have a local Hamiltonian, a bipartition of the lattice, an epsilon, and some good AGSP. Then we showed that if you take the fully mixed ground state, then the smooth max information is upper bound by this factor. It is log of d times L divided by epsilon. In the unique ground state case, the previous proof, which you just have d here without this factor. This gives us the log L issue. I will show it in the next slide. Okay, so this has two important corollaries. The first one is an upper bound for the mutual information. By choosing epsilon to be 1 over L using continuity of I, you get that this mutual information is bounded by log of L times D. And also have a Schmidt rank approximation, a low Schmidt rank approximation to the ground state. This is just given by taking this product state, which is close to the state which is near the ground state, and apply AGSP on it a few times. What you get is that this product state will approach the ground state, and you can control the Schmidt rank of the resulting state. Okay, so this has two applications. The first one for gapped Hamiltonians is known from the work of Arad et al. Is that you can have a good AGSP with D, which is order of 1, put it in the bound we got before, we get that the maximum information is order of log L over epsilon. Okay, as I showed before, choosing epsilon to be 1 over L, we get that the mutual information is order of log L, and also you get a state which is close to the ground state with a very low Schmidt rank. This polynomial in the region size divided by epsilon. In the 2D case, Anshu et al. Showed that you can have an AGSP with this factor, which is log of D, and plugging it to our result, we get that this bound, we get just a multiplicative factor, which is logarithmic with L divided by epsilon, and when plugging to the mutual information using corollary 1, it is this factor is get absorbed to this order in the exponent. If better proof will be shown in the future, then we will still have this factor. Maybe depends on the proof. So this is our result. I will not prove it, but let us finish. Future research, we would really like to use the low Schmidt rank approximation to find an MPO approximation for the ground state. This is we had a few attempts to do it, but we have problems doing it. Check relevance of a proof to resource theories. This is a very nice proof. If you go over it, you can maybe generalize the sort of product state with some convex set, like a free state. Maybe modify the proof to a steady state of Lagrangian. This would be a nice future work, and maybe use this proof to actually do the 2D frustration-free area law. Okay, you can maybe discuss this if somebody has an idea. And yeah, thank you for listening.